So first of all, I give credit to all these people over here. Just to wait a few seconds for the image to load up. So all these professors did teach me parts of this one way or another. So they did contribute to one way of thinking. And actually, I had to add one more. I believe it's Dr. Mazi R2, because we're going to use the idea of impulse to get the idea of, I'll get the name typed out eventually. But for now, I'm just going to leave it like that. And then now we're going to move on. Why Mozilla? Because I'm going to use impulse to explain the shockwave. So if you look at the idea, you might think, why can we exclude the middle portion like it's not something that is, there and you can just move on? Why? If you think about it, basically, it's the same idea as what we did with a hammer or ball, and what we did with impulse ideas. What I mean by that is, think about. Let me just erase this for now, and let me give you an idea first. Uh, Let me give you an idea of a ball falling down like this into onto some kind of table. Now I want to get information out of it to figure out something, okay? And you might be, and then you will say, yeah, let's just go to momentum equation and get to the initial and final by using an E, right? Because you're using you know what I mean, right? But if you really look at impulse, the idea is when it hits over here, the actual graph looks like this, and you take an integral of this, like numerically, whatever. But we can skip that complexity by looking at what we want in actuality. Because do we care about the force on each other? No, we don't, because this ball is going to fall off like this, and maybe you want the trajectory of that more. And the idea is similar to that concept. And then, in my opinion, this is just my opinion, they're similar concepts. And I think linking those together will help a lot in this case. What I mean by that is, if you think about it, what is important in a shock wave? Like if I were to show you this image, and then show you that this portion over here, you see a straight shock like this, and you see force going this way and that way in the end, and you see that the velocity drops over here. Do we care about how it drops in this section? I'm not sure, but for applications that I think that that this like something like this, we want the velocity on the outside to get some kind of pressure lift, right? Or something like that. So why would I want the in between of a shock wave image for certain, like I'm sure there's other situations where it's important, but not in this case, I think. It's a lot of I think here because I'm not too sure. Maybe there is a case. I can't really think of one yet. So if someone can bring that up, I would love it. Now, with that said, you can kind of see some parallels here. It's TD over here, and this is UD over here, and this is, I believe, density. So density goes up like this. And then the last one, what's the last one? Temperature, pressure really goes up. Oh, pressure goes up definitely, and then density is a little smaller one. Because pressure goes up a lot apparently, which we'll see later. I think I don't remember actually, but you can kind of see why impulse and this idea. This is how I looked at it when I first saw this idea. It's an incredible idea. I like it. It simplifies. It makes it easier for me to think about this because that's the only way I can think. No, there's a lot of ways, but this is the easiest way. And why I say momentum is think about the Navier-Stokes. We're going to the integral form, right? And that integral form is really just a momentum equation. And if that's the case, well, these equations over here is just momentum equations to the end. So thinking the same way is not a bad idea, I think. So that's why this works, I think, in my personal humble opinion. Let me just pause for a second. Okay, so with that said, let's continue. Had to move because that place, someone was doing other stuff again. Anyways, with that said, we can now look at this and say, yes, it makes sense. Now, what do you mean by that? Well, we need to look at what in the continuing takes. I can't say it correctly for some reason because I'm a little bit of what I'm doing. Okay, so we need to first write the momentum and the continuity equation in conservative form, which this thing over here. So what we do here is think about what a gradient really is. A gradient is a derivative in many forms, and that's why I write this usually in index notation because it shows off that it's a derivative. What that really means is that since this is 1D, we can get rid of that and just say, okay, this is going to be d dx, and then it's going to be rho u, and then equals 0. And then this doesn't have a time, and then we can do an integral over here to infinity and negative infinity. And wonderful, we have our first equation because we know what at infinity is going to be. It's going to be this one, and it's going to be this one, and then so on is going to be this one, and it's going to be this one over here, I believe. And you're going to get the final equation over here, which is going to be basically rho u upstream upstream minus rho d UD, and we have our first equation that equals 0, and then so forth to now have to do to remember not to be complacent. Um, I think that's it. Yeah, I think that's it. And then it is oh, it's the microphone, so that's making that noise. And then plus, I believe it was gradient dot tau, right? Am I correct? Am I not correct? Am I correct? I'm pretty sure I'm correct. If I'm wrong, I'm wrong, but gradient P. I think that's right, right? Yeah. Um, if I'm wrong, please tell me. I don't want to be wrong here. Anyways, what this does is again we have a situation where we can do d dx, and then we can do v squared over here equal, which will be plus if you move it to the other side, do it d dx pressure, and then that would be we can also do this thing, but that's mu du dx, and then there's a dx over here. Look at the what do they call it again? Look in your Navier-Stokes and go to your compressible form, and you'll see incompressible form. You'll see that it is basically a secondary, but the mu now is a little bit different because it's a gradient. You get what I mean. And now basically what you do is the integral negative infinity to infinity, and then this goes into here into negative infinity, which just cancels out, so it's going to be mu du dx. Now, I believe this one has a problem. I don't remember what's the problem. Uh, this should go away somehow. I don't remember how. Uh, I don't remember how. Hmm. This should do something, but I can't really put my finger on it. I know it does go away. Why would it be going away? Is the question. This part makes sense. This will give you P plus U square up, and then equal to the down. Let me just move it there. Down. That's fine. Well, this form should go away somehow. If you really think about, oh, there isn't a change in U when you go over here, and if you go over here. If you think about it, look far away over here to this place over here. It is constant. It is constant over here. Therefore, any gradient over there that's left over will turn into any derivative will turn into 0. So there you go. That's the solution. Woohoo! Anyways, let's move on now. We are done with this portion. Oh, energy question. I forgot the energy. Energy is a little tricky due to it being more harder. Energy is a little tricky, yes. But we will do it. So in conservative form, I believe if I may write it like this, I believe it is d if you change it, h plus p over rho. No, it is h plus v squared over 2. Why this happens is the pressure goes over here, and you find that, and now you have a plus, and then you have I believe it's d dx mu. I think it's definitely mu. uh there's a velocity again, so there's a velocity here, and dv dx, and then du. And you know this is going to be 0 if you integrate it, because the derivative survives, which in the end over here is all 0. And then you do that again with the temperature, which is d dx, and then you have k dt dx, which shows you that this temperature is constant all the infinity, negative infinity, so therefore we're fine. It's rewarding to get something out of algebra sometimes. I think it was pu plus v u squared divided by what was it again? 2, right? Is it 2? With p and then plus rho u. I mean, did they move the un out, or the u? Yeah, they moved the un out. Which, why is it minus? Even though they're trying to solve for it, it should be. Yeah, it should be. How's it minus? Oh, okay. No, I'm right. I'm right. I think I'm right. Okay, apparently you want the minus version, which fair enough. If you do the minus version, this over here, because this is minus, turns to a positive. So you can move that over here. Rho d un squared divided by rho un squared, and then this will be a 1. So minus minus, so that's -1. With that said, what can we get from here? Well, we can get not much actually right now. Yeah, U, and this is D, and this is D. Okay, so that's what we have so far. And from that, yeah, we're trying to get the Mach number out here. So, okay, so I should write this more cleaner on our row. So it's going to be P D equal PU minus rho U square U. So there's a U over here. and then we're having a row up top, and then we're trying to get Mach number of UN. So UN is this one over here. And to get the Mach number, you need the pressure, right? Usually. Usually you need a pressure. I don't see a pressure, except for this one. And then that would mean you have to divide everything by U. Oh yeah, they do that, I guess. Yeah. PU, PU, PU. And now, what else do we need for Mach number? We need Mach number means A, which you need A equals gamma RG temperature. Do we have a temperature here? No. That would mean we need this form over here because there's no temperature. We need P over P dash dU. We have that. Now we need gamma and gamma on top of each other. Yes. I think that's it. That's all we need. But wait up, wait up, wait up. You need A squared, and you only have this as this will only give you no wait, this will give you A squared. Yeah, AUN squared. The problem is the density did not go away, which is because we haven't used another equation that equals 1. And that equation is this one. If you look at the continuity, it shows U, and it shows, I believe it shows UU equal rho D UD. And if you divide that by rho U UD, that equals 1. So you can substitute 1 out. So let me just do that real quick. So rho D UD divided by rho U parentheses, and then there's going to be a U D U N, and this goes to 1, showing off that. Okay, beautiful. And now that would leave me with PD PU equal 1 minus U square alpha A square U parentheses UD UN minus 1. There we go. That's the Mach number UN square. So we have everything. Okay. I know how to do. I should be doing this later, but we'll do it soon. Yeah, I need to go and do other stuff, unfortunately.